Recording. That's fun. All right. So, the last lesson we did, thank you. The last lesson we did was on percentage composition. And I said to you at that point that we were, let's put our phones away, folks, please. I said that we were kind of stepping away from our calculations using the mole. And we were using kind of an old way in which substances were calculated, and that was percentage by mass. And it works very well. The percentage of mass of a substance is constant for that substance, and therefore it can be used to identify it. And it was used to identify it in the past. And then the concept of masses came along, and I've talked to you about that, right? Chemists did experiments where they weighed a whole bunch of stuff, and they decided, hey, let's let the mass of hydrogen always be 1, and then we'll compare everything else to that, which resulted in very good numbers. And then they had this thing called gram molecular weight, which they knew that they could use this to kind of tell what the ratio of something was, and they didn't know what that something was. What it was originally was gases. It was ratios of volumes of gases, and I've already mentioned to you that our ideas of molecules and atoms and little things came from the study of gases. So what we're still doing in this lesson is we're kind of working our way through the way chemists would have originally determined formulas. So what would they have done to determine a formula when they were starting to understand this idea of molecules, et cetera, et cetera? So we're going to use our concept of the mole to do this. They would have used this idea of gram molecular weight, which dealt with volumes, but it really is the same thing. So I'm teaching you kind of the original way in which scientists determined chemical formulas for the first time, not based on electrons and orbits and charges. That's theory, that's from Bohr, but based on experimental evidence. So you can see the title of this is, well, the first title is Empirical Formulas, all right? And I've been telling you all the way along in this course, there's two ways in which we can explain things. We can explain them theoretically, or we can explain it based on experimental data. So the first formulas that were calculated were based on observation or experimental data, and therefore they were called empirical. Formulas obtained from experimental data. We're going to talk how this relates then to molecular formulas. I'm going to talk a little bit about the difference to begin with, and then I'm going to show you how we calculate it. Okay, now, the definition for an empirical formula has changed over the years. You can write down this definition of an empirical formula, and then I will explain to you what I mean by this. So this is a weird definition. The definition of an empirical formula is the simplest whole number ratio of the atoms in the compound. It has atoms in it, which means it's almost like a theoretical definition for empirical, which seems a little silly. Again, like I said, the empirical formula was first determined by experiment. We're going to use experimental data to determine empirical formulas. But now we know the empirical formula to represent the simplest ratio of the atoms in a substance. So let me give you some examples of that. Examples. When we do an ionic compound, let's say I am doing lead 4 carbonate, all right? Lead 4 carbonate. When we get the formula, right, we've got the lead, and we've got the carbonate, and this is 2 and this is 4, right? and we get rid of the common factor of 2. So lead 4 carbonate then is written as that because we canceled out the common factor. That is the simplest ratio of the atoms in the substance lead 4 carbonate, because we cancel out any common factors and we always bring it down into a simplest ratio. I could pick another ionic compound. It doesn't make any difference. Copper 2 oxide, CuO, 2 and 2. Bring it down to the simplest whole number ratio. This is also an empirical formula. All ionic compounds are always expressed in their empirical formula because we always cancel out any common factor. So I'm going to make a little note of this. Note, all ionic compounds are in their empirical, I spell empirical wrong all the time, empirical formula. By definition, ionic compounds, when we cancel out any common factors, results in their empirical formula. Okay? Now, molecules, it's different. All right? For molecules, it's vastly different. I've got a different slide to talk about how we deal with molecules. So let's talk about how we deal with molecules. Molecular formulas. And I have a table there with a bunch of examples to illustrate the difference. So you can write that down. You don't necessarily need the chart. You don't need to bust out a ruler. That's up to you. Carson forgot her glasses. You want to swap out? I can move the other guys back. I'm going to watch your squint whole class long. Do you want me to read it? Represents the actual number and kind of atoms in a molecule. Yeah, that's right. At this point, Carson is the star. Well, the co-star. I'm the star. I know I couldn't make it in Hollywood, so teaching guarantees me an audience every day.
Well, like 20 views on your YouTube channel.
Yes, 20, correct. Except for Petrus's silo falling down, if you've ever checked out my YouTube channel. A silo at his house was taken down, and I put it on my YouTube channel when it came down. It's entertaining. It's got like 500 views. Okay. So for molecules, it's a different thing. Some of them are in their simplest whole number ratio, like water. Water is in the simplest whole number ratio. I cannot cancel out a common factor out of water. So its empirical is also H2O. And you don't have to write this down, but that's because molecules are different than ionic compounds in that they're not a ratio of ions, they're atoms bonded to other atoms. So hydrogen peroxide, which is H2O2, has an extra O, so it gets a per on the front end, just like the per we use when we do oxyanions. Its empirical formula would be HO, because we could cancel out a common factor. But its molecule is actually 2 units of those HO. Now, if you were a chemist in the early 1800s and this idea of atoms was just being formed, then, and you were beginning to figure out empirical formulas based on experimental data, for hydrogen peroxide, you would have got a formula of HO. You would have no knowledge that it was made up of 2 of those things stuck together. That came later on when they were doing other techniques. Carbon dioxide, CO2, is the empirical formula, because I can't cancel anything out. What would be the empirical formula for C8H18? We want to reduce it down to its lowest kind of set of numbers. Yep. I don't think so. Divide by 2. Oh, yeah, I think it is. You got it. Divide by 2 each, right? C4H9. I like that. I do. It's good. Can't divide off anymore. Ethine. That's that acetylene. That was the one that made the big bang when I did the demonstration. This was pretty straightforward. I can cancel out a 2, CH. But then there's other molecules like benzene. Benzene's been in the news recently about a possible benzene release that is being affecting the Angenon reserve, which is unfortunate. Hopefully they can get it cleaned up. So benzene is a toxic chemical, but it also would be CH, all right? And so chemists in the early 1800s, when they were calculating percent compositions, these two things would have the same percent composition. And therefore, according to the law of constant composition, are they the same chemical? Well, they have very different properties. Ethine is a gas. This is a liquid. So they're very different things. So chemists realized that there were issues with the idea of percent composition. Okay? All right? So empirical formulas are the simplest ratio. For ionic compounds, they're already in empirical formulas. For molecular compounds, we need to do another step to figure out what the molecular formula is. Today, I'm going to teach you how to determine empirical formulas, and then on Monday, I'll add the extra step to determine the molecular formulas. Okay, let's do some examples. Don't write that down. I already wrote that down. Same percent composition. Okay, that's good. We already wrote that down as well. Chemical formulas for ionic compounds are the same. There's a couple of practice problems that simply asks you to, is this an empirical or a molecular? There's no calculation in those questions, but it is worth writing down. It is worth something for you to do. But it isn't a calculate the empirical formula type question. That's just to check that you understand the difference between an empirical versus a molecular. And now we're going to do the examples. Now on, I don't know, is it the next slide? No. In a couple of slides, there's a bunch of rules on how to calculate it. And I'm not going to have you write those rules down. I'm going to incorporate the rules in the first question that we do to kind of show you how we do it as we do it. And then when we continue on, you don't have to write those rules down each time. Now, before that, I just want to talk a little bit about a chemical formula. You don't need to write down interpreting chemical formulas. You don't even need to write this down at all. This is just for me to think about. Let's go back to that example, lead 4 carbonate. So when we look at a chemical formula, these numbers have meaning, and you guys, I think you should know what those numbers mean. What does that number mean? What does the 1 beside the lead and the 3 and the 2 to make 6? What do all these numbers mean? Like what does that 6 represent in this formula? It's a very simple answer. What does it represent? It's going to be embarrassing. Thank you, because we're recording this. Yep.
How many oxygens are we calling?
How many oxygen atoms? 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 So how many oxygen atoms are in that particular thing? So in this case, this is essentially saying that we've got 1 atom of Pb, right? And what? 2 atoms of carbon, and then 6 atoms of oxygen, right? I think you guys know that that's what that representation is. We count the atoms. Now, we already know that calculating atoms is tricky. We could try to calculate entities, because entities are atoms. but that's really kind of a pain. So if I had, let's say I had 1 mole of this stuff, all right? Let's say I had an entire mole of lead-2 carbonate, and I took all of the atoms off of that entire mole of stuff. Then it would become, I would have 1 mole of lead. And we did this kind of with that little extra factor, right? Remember we said you can pull off those atoms. And it would mean that I would have 2 moles of carbon and 6 moles of oxygen. So if I do a calculation where I could determine the number of moles of each of those atoms in that sample of material, I will also have the formula. So it's more convenient for us to calculate in moles. Because if I have an experiment where I've weighed out the amount of lead in grams, I have a conversion factor that can convert grams to moles. And then I can think of it in terms of moles. Okay. So that's what we want to do. That's our plan. When we have a question, we want to figure out how many moles of each of those atoms we have, and that will tell us our formula. Now again, here's the rules. Don't write it down. You can make reference to this. You can go back to Google Classroom and find this online, but I'm going to just do this as I go. We're going to start by calculating from percentages, because we're going to have lots of percentages. When we have a percentage, we're going to turn the percents into grams. We're going to pretend we have a sample that's 100 grams in size. So if I have a 100-gram sample and 29% of it is lead, then I have 29 grams of lead, because I'm just switching the percentage for grams. Then we're going to determine the moles using the molar mass. And then we will have a ratio of the moles. Then we'll know what that ratio of moles is in order for us to determine the formula. Okay, no need to write that down. I'm going to write it down as we go through the problem. So you can write down e.g., you don't even need to write that down, just write this question down. Now I am going to attempt to do this question all on the smart board. Usually I do it on the chalkboard, but I'm making the video, so let's see if we can squeeze it all in. You are going to need molar masses for this. So for all of you high maintenance people, say hi, was nice, since I'm recording. Didn't call you slackers. You're going to need a periodic table. Okay. So an experiment was done, maybe like the experiment we did yesterday. Yesterday we only determined the percentage composition of carbon, but let's say someone worked hard in the laboratory, determined the percentages of sodium, chlorine, and oxygen in some compound. All right? Okay? I don't want to leave anybody behind if you're just writing the question down, because these initial steps, we want to make sure everybody hears them. So the first step was to assume 100 grams. So what I like to do is I'm going to go way off to the left here so I've got enough room. I'm going to start with Na. All right? And instead of writing 21.6%, I write, I write 21.6 grams. Okay? So in this case, what did I do for step 1? Change percent to grams. Step 1. And I'm going to do it for the rest of them, but I want to go through the next step first. We want to calculate the number of moles from those grams. I'm going to put this way off to the side here because I'm squished way over there. But we know that molar mass is equal to mass over moles. If I wanted to find the moles, what would be the equation? If I wanted to find the moles and I had to rearrange that, what would the equation be? Yep. Molar mass, mass over molar mass. Excellent. So if I want to turn that 21.6 into moles, I'm going to divide by the molar mass. Okay? So now I'm going to my periodic table for sodium. And am I seeing 23.0 or 23.1? Is it 0? 23.0 grams per mole. Step 2, divide by molar mass. All right? And equals. Let's do that for the rest of the elements in this particular question. Chlorine. Turn it to grams. 33.3. Divide by its molar mass. 35.5. 35.5 grams per mole. Equals. And oxygen. Oh. 45.1 grams. Divided by 16.0 grams per mole. Then now I await your calculating. I want 3 digits, which means it'll likely be point or 0 point something, something, something. All right? 3 digits. And I will take your numbers when you got them. Yep, what do you got? 0.939 moles. Perfect. And I will continue to take them when you've got them. Yep, what do you got? 0.938 moles. 2.819, that's an extra digit, but that's fine. I like extra digits, moles. Make sure we've got these all correct, because if we get a mistake at this point, the whole thing falls apart. Did we like those? Okay? All right, excellent. Now, at this point in the lesson, I always make a joke. And so don't write this down. I say, oh, look, we found the ratio of the moles. The formula is Na 0.939, Cl 0.938, O 2.819. There's the chemical formula. And you should all look at that and go, that's not a proper chemical formula. You can't have that. You can't have decimals in it. They've got to be whole numbers. They must be a whole number ratio. So we do have the ratio, but now we have to make them into whole numbers. All right? We have to turn them into whole number ratios. So step 3 is to divide all the numbers by the smallest number to force it to become 1, and then we get the ratio of the rest based on that. So step 3, divide all by the smallest. Okay? So in this case, it looks like it's 0.938. So I've got 0.939 divided by 0.938, and that is going to be really close to 1. It's going to be 1.0 something. 0.938 divided by 0.938, that is the smallest. It is 1. And 2.819 divided by 0.938 is I can't do that in my head. 3? Really close to 3. 3. All right. Perfect. We now have the simplest whole number ratio. Therefore, the empirical formula is, and I'm not going to put an equal sign. It's not a number. I'm just going to put the dots there, is Na1Cl1O3. Okay? It's pretty straightforward. When we're given a percentage, we divide by its molar mass to turn it into moles. We do it for all of them. We then divide by the smallest number in order to make it into a whole number ratio, and then we have it. I've got to go through 3 or 4 more other examples because there are a few that have little twists in them that I got to show you how to do. But that's the basics. We do them all the same way. All right, let's do another one. Now at this stage, I'm hoping you can go ahead of me. This is the type of thing where you've got a pencil, you're going to use the same steps. This time I've got some sodium, some chromium, and some oxygen. Find the moles, divide by the smallest, and then I think this one has a wrinkle in it where we have to talk about what to do to fix something. Sometimes it doesn't work out as nicely as we want. So the question asks, not that anybody needs me to read it because they can't see it, a compound contains 17.6% sodium. You're supposed to be writing, Carson, at this point. Can't see and can't write as I'm talking. That's really tough. Don't wait for me. Na, 17.6 grams divided by the molar mass. Cr, 39.7 grams divided by its molar mass. Oxygen, 42.7 grams divided by its molar mass. And carrying that 1 decimal becomes quite important for these because when we divide by the lowest number, if things don't work out perfectly, they get a little goofy. 23.0. Notice I didn't write grams per mole this time. Now you should, but if you don't, I'm not going to take any marks away. Chromium is what, 51.99, so 52. 52, 16. I will take some of those numbers when you get them. What do you got? Just one? Oh, that's okay. You got it and you shared it with me. Good job. That's exactly what I asked for. 0.763. Sorry, I missed that last. 67. Again, hopefully you're just a little bit ahead of me. If you're a little bit behind, make sure you can get those numbers, right? Make sure you're able to get those numbers. We're now going to divide by the smallest, 0.763 divided by 0.763 equals 1. 0.765 divided by 0.763 is essentially 1. 2.67 divided by 0.763 is, and what do we get? What's that? 3.5. Okay, 3.5. All right. So sometimes you might get something that isn't a whole number. Now, what does this mean? Essentially, this means that there isn't a 1 in this formula. It means that the simplest whole ratio doesn't have any 1s in it. So what we have to do is we have to bring the ratio back up. We have to bring the ratio up a little larger to get rid of that 0.5. And in order to get rid of a 0.5, we're going to double everything. All right? Now I'm going to perform an illegal mathematical move here. And so don't tell the math people. But it would be very incorrect for me to just slap on the end a times 2, a times 2, and a times 2, because that would make this equation a fallacy. It wouldn't be true anymore because it would essentially say 1 is equal to 2. But don't tell anybody, but that's what we're going to do. We're just going to put a little factor on the end of it. And then that's going to make that a 2, that's going to make that a 2, and that's going to make that a 7. Okay? And now we've done it. We've now created that whole number ratio again, right? It has to be a whole number ratio, and that's why that 3.5 is not allowed. So now I can write that this is Na2 Cr 207. All right, and I think if we check that, that's sodium dichromate or something like that. Okay? Now, I'm going to add a note on the end of this. Sometimes there isn't even just 2's in it. Sometimes you've got something where the smallest ratio has 3's in it. Okay? So, let's write down what we did. If you end up with an x.5, and that's a terrible 5. Try that again. If you end up with, say, an x.5, all right? And I know x isn't the best thing to use because I'm going to say multiply by 2. And that multiplication is going to look like an x. So make sure you understand what I'm saying. If you get a something 0.5 times 2, double everything. The little dot, do you think that's the difference? Yeah, but I got a dot here for the x.5, the something 0.5. I think that would be more confusing. But thank you for your suggestion. I could have an x point. What's my next one down? I've seen an x.333. What am I going to multiply that by to get rid of a 0.333? Somebody say it back there? Yeah. So it's like 1/3, right? So I'm going to multiply that by 3. Okay? That also works for x.666. I've seen that as well. That's like a half and a third. And then again, when you multiply by 3, it takes care of both. I've seen an x.25. What would I multiply it by to get rid of an x.25? Yep, 4 times 4. And I have seen one where I've seen an x.2. What do I need to multiply them by to get rid of the x.2? 5. Okay, times 5. So that's just warning you that you could have, after you're done the division, something point, something, 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 and that tells you what to do with it. Okay? All right? And it simply means that there isn't a 1 in that particular formula. Yes, you can. Let's do a couple more examples. So this is my last example that I'm going to do with percents, and then we'll talk about examples that we do with just experimental data like grams. And it's easier than you think. The steps are exactly the same. So just a few more examples here to finish this off, and then I have a sheet for you to work on. No, this is not what we do for our lab. Look at the previous lesson. When I set you to do homework, I will come around. And for video purposes, that's Caitlin, who is very confused about something. But she's number 1. Just keep that in mind. Carbon, 40 grams. Oxygen, 53. Hydrogen, 6.7. Divide by molar mass, divide by smallest numbers, if you get a 0.5 or a 0.33 or a multiply by the appropriate value, get the empirical formula. I don't think I did it in the last one. Notice how I didn't write moles last time. I don't need to see mole. I don't need to see all those units. As long as you know what you're doing, as long as you can get the answer, I'm okay with that. Some teachers want always the units and want everything to look the way it's supposed to. I just want to be able to see that I can see what steps you're doing and understand that you understand. If you drop a unit or two here or there, it's not a big deal. Mm-hmm. 3.33, 3.31. This looks like a 112. Pretty straightforward. Do we not like those numbers?
I got a 4 at the end of it. When you have to round.
This one?
That one you get another 2. No, I got 3.33. Yeah, I got 3.33.
We like that? So this is looking very much, and again, do humor me with this step, okay? I know sometimes it's like, oh, why am I writing this out? I can see that it's equal to 1, but still, when doing these questions, humor me on that one, 3.33. That's a 2, isn't it? It's a 2? Yeah. So this one was straightforward. We didn't have any curves or tricks to that. This is going to be C. Typically, we put the H first, but that's okay. I'm okay with it this way. OH2. That's just a funny way to write that molecule. All right? Okay, now, in these cases, we've started with percentages. And that means someone did an experiment, found the percentages, posted them or shared them with whomever, like experimentally, and then that allowed us to take those percentages, turn them back into grams, and continue. We can also work straight from masses or experimental data. All right, so you can write that one down. And as you're writing it down, I am going to give you the worksheet in which I speak of. You don't need to write down the fact that this is number 26 on the worksheet. So this is an old sheet that I got years ago out of a book that when I started teaching had just a bunch of extra practice problems for various types of things. And this is a very nice straightforward sheet that deals with empirical formulas. On the front, it's pretty well all percentages. On the back, from 27 to 35, it's questions that involve masses that come from experiments. I can't just throw together an empirical formula problem because it has to be based on a real chemical. I have to end up with the right numbers at the end. So I'm just too lazy to generate my own question. That my last two examples I just took off of this sheet. So if you get down to question 26, you will have done it. All right? So that's what that means. You're welcome. I will also post the solutions to these. Now, the misconception about a question like this is that this is harder because it's not nice percentages, but it's actually easier. I have had students turn the grams into percentages by adding them all up into a total and turning it into a percentage composition. But you don't need to do that. The ratio is already in those numbers. The only difference between a question like this and the last one is we don't have a sample that's 100 grams in size. We have a sample that is like 18 plus 7 and a bit plus 14 in size. But we do it the same way. So in this case, I'm starting with potassium. Oh, I don't put an equal sign normally because it's not a calculation. But I've got potassium, and I have 17.96 grams, and I am going to divide by the molar mass of potassium, and I'm going to do the calculation the exact same way. So it's actually easier. I don't even have to think about turning it into grams. I am just proceeding. Sulfur, and I don't know the molar mass of potassium offhand, that's why I'm not writing it down yet. 7.35 grams divided by, oh, that one I do know, 32.0. And oxygen, 32.1. Excellent, thank you very much. Because it does become important, it'll affect that last little decimal, and it can then affect that if you got to double it or triple it, et cetera, it can have a little effect on that. 32.1, and oxygen is 14.7, and that's a 16.0 grams per mole. Dividing by the smallest number, multiplying if we need to, and we get the empirical formula. Okay? And I guess if I'm writing a little rule here, just use, I was going to write use grams and I put it together. Just use the grams as is, right? You don't need to do anything fancy with it. Just use whatever grams you've got. Potassium is 39.1. 39.1. And I do have a second example, which is another question off of the sheet. I don't think we need a second example. I think this explains what needs to be done if I give you a question that involves just grams. Hunter has his hands in his pockets, indicating that he's done some math. What do you got? 495, 459, 459. Yep, N. 229. 0.919, 0.229 divided by 0.2291. 0.459 divided by 0.2292. 2? It's close to 2. 0.919 divided by 0.229. That 3 and a bit? 4? 4. No points, nothing on that. I think my last one probably has another one that has a point something on it. But this doesn't have it. K2S104 is the empirical formula. I don't think we need to do any more. What's our time? 33. Gives you time to practice lots of these. Yep. Oh, this is, every time. Every time. Yes. Oh, amazing. Let me stop my recording before I make any comments that I regret.